All right, so the very last part of this chapter is to really talk through the pipelining, how pipelining impacts the MIPS microarchitecture. So just like we looked at earlier, we essentially can start off with 5 stages. So the instruction fetch from memory, decoding of the instructions, and then the execution, memory access, and then the write back. So let's just say, for instance, that we assume that a register read or write takes 100 picoseconds, and that all the other stages take 200 picoseconds. So here's how we might see the total execution of a number of instructions like load word, store word, or one of the register formats like add. So you can see for a load word, for instance, 200 seconds to fetch, 100 seconds to read, picoseconds, 200 picoseconds to do the ALU, 200 to access memory, because remember we're loading. So we're going to go out and read memory and bring it back. And then to write that result back into the register. Okay, you can see for the store, I don't need to write something back into the register because I'm storing it in the memory. Okay, so you can see a total amount of time for a number of different operations can change depending on which hardware they actually need. And this would be like the best case, right? In pipelining, however, what we need to do is we need to essentially look at all the stages. All right, so here you can see like a load would take 800 picoseconds based on what we were looking at here, right? For a single instruction, right? It's going to take 800 picoseconds. However, if we're doing pipelining, recall that we always need to make sure that our stages take the exact amount of time. So even though we have these register stages that only take, in this case, right, this register stage takes 100 picoseconds here and here, we essentially need to stall a little bit here to make the, so we don't get too far ahead of ourselves or because of the ALU and the instruction fetch taking 200 picoseconds in that case. So you can see in the end, yes, a single instruction is still going to take 2, 4, 6, 8. It's actually 1,000 picoseconds. So because we have to add these 2 stalls to make sure that the register cycles for the instruction decode and register read and the write back to register, and those are on that same 200 picosecond pipelining phase. But the main difference is that we're actually getting a new instruction completed every 200 picoseconds. So yes, we have to stall a little bit. A single instruction takes 1,000 picoseconds in the pipeline version, but then we're pumping them out every 200 picoseconds. So that would be the major gain. So as we've talked about earlier, I won't go into detail here because we've kind of broken this down a little bit, but hazards are a very real thing that we have to think about, right? We can't just always issue the next instruction immediately, after that 200 picosecond pipeline cycle is done. Why can't we? Well, we have structural hazards, data hazards, and control hazards. Okay, so we've already talked about these data hazards being the main one, data and structure, in some sense, kind of the same thing. But the idea behind structural hazard is hey, there's a conflict for a use of a resource, right? I have 2 things that maybe want to use the ALU at the same time, and they can't. Okay. So for instance, right, maybe I have a load store which requires data access, and I have an instruction fetch which has requires data access at the same time. So those are things that we need to think about, because the load store is going to try to access some kind of program data versus instruction fetch is going to access the instruction memory. So a lot of times systems will have separate instruction and data memories to avoid that conflict right there. So instead of storing everything in one kind of granular memory that has data and instructions interspersed with one another, they'll have 2 separate areas where you can access those concurrently. So here's a data hazard, and we walk through this in the IJVM in pretty good detail. But here's kind of the high-level example with kind of looking at it with MIPS code, right? We have an add, S0 equals T0 plus T1. And then my very next instruction wants to use that S0 result as an operand. Well, if we look at our add instruction and we pipeline it, we can see it has these 5 stages. But I can't actually access that S0 until it is written back to the register. So you can see basically here I have to add 2 stalls, because once it's written back to the register, then it will be available to pass into the execution unit. Okay. There's a number of tricks that we can do. Okay, so maybe forwarding, for instance. And the idea here is that I add special connections in my data path, maybe from the execution unit, and I just cycle that right back in to its inputs, so the output to the input. So the idea would be that I can, instead of having to go through this stage, and I'll still send the data forward through this pipeline, but if I can figure out that that next instruction is going to use that output of the ALU, I can just feed it back directly into that instruction, and that could eliminate that those 2 stalls we saw in the last slide. Likewise, I could, add some extra hardware to maybe push that back a stage if need be. So this is our MIPS data path, and you can see here we have it broken down into the 5 stages of the pipeline. So you can see over here we have the instruction fetch stuff that we talked about earlier. We have the instruction decode and register file read, so those are kind of combined into the same thing. And our IJVM, the instruction decode, was mostly dealing with that the micro instructions, which we don't really have here in MIPS. So it's really just kind of decoding these registers and sending them out onto the bus. We have the A and the B bus in the IJVM. It's just, register 1 and register 2 buses here. And then we do the execution. So you can see the ALU is in that phase. And then the memory access, again, here's our data memory. You can see our instruction memory is way back here, so we don't have that resource hazard that we just talked about. We have all of our memory broken into those 2 kind of granular instructions and data. And then we have the write back stage, which you can see it really just kind of cycles back into that write register, and the data is passed back that way. So how would I pipeline this? Well, just the same way as the IJVM. I basically toss latches in between where those stages are. So if we were to look at a load, for instance, okay, you can see kind of the beginning and the end of that phase. So the load is basically taking, let's just imagine a load, right? A load is taking something out of memory. So it's already kind of latched into my memory, and it's putting it alongside the data path, and it's going to latch it into this pipeline stage, or the instruction fetch, okay? And then the next cycle, right, it's going to latch it out of that kind of IF instruction fetch, instruction decode latch combo there. It's going to latch it out, all right? And you can see kind of in this case, it's going to, that will allow me to access certain registers, my 2 registers, for instance. Well, I guess it's just 1 register really if it's a load. And that's going to unlatch that particular register value into the next pipeline latch, all right? And then once that's done, right, I latch it out of that pipeline stage, send it through the ALU. Like for instance, if there's a offset to that load that I want to load some register +4 or register +8. So I'm going to compute that particular address at the ALU of where I'm going to load from. And then I latch that into the next latch. And then finally, this address is pulled out of that pipeline stage latch, and that is fed directly into the address of the data memory, and the value in that memory is eventually flows out of the memory into the final pipeline latch here. And then the last stage, of course, would be to do the write back stage. Okay, so the write back stage we come out of that last latch, which would be essentially the C latch. If you're thinking IJVM, flows all the way around back into the data register. Okay. And just finally, these are just another depiction of what we've already seen with pipelining. This is basically showing a few instructions being executed from a resource usage perspective. So here's the different clock cycles. And you can see, once we get to clock cycle 5, because we have 5 stages, you see 1, 2, 3, 4, 5. There's essentially 5 different things going on. 5 different resources that are kind of being utilized at this point. And that's going to be true from here on out. If we want to look at it from the kind of the traditional form, we might just actually list, in boxes the the actual stages. So instruction fetch, instruction decode, execution, data access, and write back. Now, all of the, one of these instructions might not particularly need something to occur, but the data, like for instance, let's say a store, store. I guess we don't have a store up here, but if we had a store, it wouldn't necessarily need the write back stage. Okay, so I mean, keep that in mind. It wouldn't need it, but it's still, the data is still going to have to kind of flow through that circuitry. All right, and that's it. So that was just kind of showing you how everything we've looked at with the IJVM, just kind of at a high level, how that applies to MIPS and how you basically put the hardware in there. And at the end of the day, you're just putting latches in at key places where you have your pipeline divisions. All right, thanks.